see that Aaron is on the call. Thanks, Aaron, for letting me switch.
Okay, would you like to test the screen share? Do we have that set up yet?
I did that right away.
So in the bottom is a share screen.
Let me just optimize for video clip.
And to everyone in the audience, we'll get started in just a few minutes.
Does this
All right,
work?
that looks great.
Okay, cool.
All right, and we have a slot for about 25 minutes. So.
Yeah, just let me know as I go.
Okay.
Or maybe I should put a timer. I don't know. Is there a timer in Zoom?
It's 2 o'clock. Oh, sorry, I'm not quite sure what time you're on. It's 5 p.m. PST. That's the conference time.
Yeah, just don't be shy. Just let me know.
All right. So I'll
minutes.
give you a 5-minute warning. All right.
Sure.
So we are very pleased to welcome Sanya Fiedler here. Sanya is an assistant professor at the University of Toronto, director of AI at NVIDIA, and also a member of the Vector Institute. She works a lot on 2D and 3D object detection, particularly scalable like multi-class detection or 3D scene understanding. And some of the recent work on content creation that you might have seen of Sanya's may be to do with synthetic dataset generation, or even there's this paper that's coming up at CVPR about learning to create game engines, Game GAN. So we're very excited to have Sanya here to talk to us. So without further ado, please let's all welcome Sanya.
Hi guys, can you hear me? Oops, sorry.
Yeah, that's the alarm for its time.
Alarm, not the timer. All right, so thank you for inviting me to this workshop. I'm really excited to see all the talks. So I'm going to talk to you about today about our efforts on developing AI tools for 3D content creation. And that has been mainly done in my NVIDIA lab that I lead here in Toronto. All right. So 3D content is basically everywhere. It's in a lot of different applications. For example, architectures, architects, designers would design floor plans and put furniture inside. In gaming, a lot of new games are 3D with very rich content. And even in film, even in films that we don't necessarily know, there is a lot of graphics, there's a lot of 3D content, just because directors these days want too many things out of both actors and animals. So you need to actually generate this content. And as we know these days, due to the current situation, there's actually increased interest in VR, AR, where maybe you want to have a tiger in your room or something. And then, of course, in healthcare, 3D is actually also very important for something like simulation of operations, so the doctor can practice in advance how to perform an operation. And what I'm particularly excited about is 3D for robotics. So simulation is also key in robotics, right? Because you can't really deploy robots before you substantially test them in all sorts of different challenging environments. And I like robotics or robotic simulation because it subsumes all the 3D content creation problems from all these different applications, in a sense that you need to create environments or static scenes, 3D content like objects and assets. All the objects need to be dynamic, they need to move in various challenging behaviors, and NVIDIA has been putting a lot of effort into designing these simulators, particularly for driving and then for robotics, household robots, house robots. And the cool part about simulation is that you can get, I don't know whether you see the videos.
Audio is too loud.
All right, I'll stop it here. So one cool part about simulation is that all ground truth comes for free because you can just render it, right? And you can have different type of ground truth, like semantic segmentation, lanes, but also some ground truth that you can't label by hand on real data, like normals, depth, flow, materials, and so on. Now, one of the main problems in content creation is that manual creation, which is basically what people are doing these days, is very slow. So in this example, we ask an artist here in the NVIDIA Toronto lab to try to recreate the scene above, which is a kitty scene. And we gave him all the assets, so he didn't need to design cars or whatever. He just needed to place them in a way that would match the scene above. And it took him 5 hours to do so. And this is one single scene. So you can imagine that this is actually a bottleneck in the current workflows. And maybe we want to design some sort of AI that can speed up 3D content creation. Right, so there is a couple of problems that I think we should design AI tools for. Right, so we want to help or assist artists to create worlds. So different scene layouts, how the objects are placed, as well as the assets themselves. So right now everyone is stuck with ShapeNet, right? But maybe we want to have richer objects, a wider variety of classes. Scenarios, which basically tackle the dynamic aspects of scenes, so different behaviors, but also animation of articulated objects. And I think because this is hard, plus you want to still give some creative tools or creative control to the artist, you want to have interactive methods. So you want the artist to actually have a lot of control, just not let them do all the boring stuff. It takes a lot of time. So before I start, I just wanted to point to our recently released 3D deep learning library, which has all these kind of core functionalities for loading the popular benchmarks. It also features all these different 3D representations, their conversions, evaluation metrics, and it also has like a differentiable renderer inside our own and a couple of others. So it's a cool library. We're gonna make a next big release probably end of August, which is gonna feature some really nice visualization tools as well, both for learning and like just visualizing outputs. I invite everyone to check it out. All right, so let's first talk about some of our work on synthesizing worlds. So here I mean more about static scenes and not dynamic objects. So we have a couple of different works on this domain. And today I'll mainly talk about MetaSim, which is trying to create scenes for dataset creation, and also its new version, MetaSim 2, which is still in submission, that tries to go beyond what we did in the initial paper. All right, so how can you do scene composition? And this is actually a standard way how to do it in games, is that you define it with some sort of probabilistic grammar. So let's say if you take a traffic scene, you would first place the road, and then decide how many lanes, place the lanes, maybe they're parallel, sidewalk on the side, on every lane you would place cars, and so on, right? So essentially sampling from this probabilistic grammar, you get a tree. At each node, you define a class or a car or a lane, and each node also has an attribute, which means that location of the object, pose, color, whatever you can think of that basically tells you what you need to render in each position. And these are typically called scene graphs. So here I'm just showing one example of how scene is slowly sampled from probabilistic grammar. And the attributes here are sampled from random probability distribution. We didn't really tune them. But this typically needs to be done, right? So if an artist has a particular city in mind that they want to model, like New York or some city from Europe, then you need to decide on very carefully decide on what kind of probability distribution you want for each of the attributes, such that the scenes that you generate actually look like the target data. So for us, in computer vision, if you want to, let's say, have a really good object detector for that's going to work on kitty, you actually want to synthesize scenes and data, label data, that's going to resemble Germany, right? So kitty scenes. And this is what we're trying to address here. So we want to kind of automatically learn those probability distributions for the attributes. And we call this MetaSim. And basically, MetaSim has 3 carefully designed stages of how you can basically learn this model. So in the first step, we're essentially just learning to auto-encode. So we're sampling scenes from this probabilistic grammar, which is just like a prior for the attributes. And we're going to sample a full bunch of scenes. And the structure of those scene graphs are going to kept the same across training, but we're going to be learning to, or we're going to be modifying the attributes. We're going to try to rotate car, maybe recolor them, and so on. Okay, so first we sample this these scene graphs. Then we're going to encode these scene graphs with like a graph neural net, graph convolution neural net in our case. And in the first step, we're just going to make this GCN auto-encode these graphs. So basically, at every node, we're going to try to repredict the attributes. So, you know, whatever location, color, or whatever. Okay, so this is our first training procedure. In the next step, we're going to try to bring the target real data in the loop. So in this case, we want to create scenes that resemble Kitty. So we're going to just throw a lot of different random samples from the Kitty data set. And we're going to try to learn, so our GCN is going to try to modify the attributes such that the rendered scene are going to look like Kitty, essentially. Okay, and we do this with a distribution matching loss. So essentially what we do is, you know, sample a bunch of different scene graphs. The GCN is going to try to predict new attributes. We render them, and now we have a batch of real data, a batch of synthesized data, and we compute similarity metrics between these 2 batches. And we use here MMD, so maximum mean discrepancy, to compare these images. And this loss can be propagated back to the GCN. And because the renderer here is non-differentiable, we just use numerical gradients here to train this. And then there is a last optional step, which is, imagine that I want to actually have this particular object detector that I want to create the data for. So I want to create a data that's going to be somehow optimized for my task and for my network, so that when I train on the synthetic data, I'm going to do the best as I can on real Kitty data. And here, basically, what we do is we're basically training the task network, as we call it. So here would be object detector during training. So we generate some data set sample for the current GCN. We train this task network on this data. We get a score on the real data. And then we propagate that score back to the GCN. So we're basically optimizing for the target performance. So some results on the right, I'm showing a couple of samples from the Kitty data set. On the left are the samples from the initial probabilistic grammar, the kind of, you know, just uniformly or randomly set parameters. And in the middle are basically scenes that are optimized with MetaSim. So you can see that the cars become aligned with roads, and they also come closer to the camera, which probably seems like it's a bias in Kitty. Here I'm going to show how MetaSim is modifying the scenes during training. So it's basically learning how to adjust these scenes such that we get highly similar scenes to Kitty. And we're modifying cars, we're modifying pedestrians and houses. You can see that during training things are being moved. And of course, we're doing it for a large sample. It's a generative model. We can sample as much data as we want to create our synthetic data set. All right, so what was missing in the first approach is the fact that we were relying on these initial trees, on the structure of these trees that we sampled. So we were only learning the distribution for the parameters. But basically, you can think of the structure. There was a prior on the kind of structures you would see. Okay, and ideally, we would also want to optimize that, because maybe in New York you have a lot more cars, in some village you have a lot less, and we don't want to tune those probabilities as well. Okay, so we're going to employ here probabilistic context-free grammar. We're basically, when you have a grammar syntax, which I'm showing here on the left, we want to learn a generative model that is going to produce strings that conform to this grammar. Okay, I'm going to tell you a little bit about how we're training this. So in a context-free grammar, you have symbols and you have rules. and you have non-terminal and you have terminal symbols. So for each non-terminal symbol, a rule essentially tells you how do you expand it into a new set of symbols until you basically reach a terminal node. Okay? And in probabilistic context-free grammar, you have a probability defined for each of the rules. And what we want to do here is learn those probabilities. So in our generative model, you sample a latent vector, and then we're going to map this latent vector into unnormalized probabilities for each of the rules. And we're going to do this in an autoregressive fashion with an RNN. So essentially, at each step, you're sampling a rule, taking that rule, and then that gives you a symbol, and then you continue sampling the rules. Okay, and here the mask is essentially saying, for this particular symbol, which are the valid rules I can sample. Okay, so the image is basically created by sampling these rules, which tell you the structure, and then you're sampling the attributes for each of the nodes, and then you can render the image. Okay, so know that this generative process has essentially a lot of discrete steps, a lot of discrete sampling steps, and as well as the renderer is non-differentiable. So this is actually very hard to train, and we tried doing it in the same way as we did with the original metasim, so just MMD loss, and it didn't work. And I think one of the reasons was that MMD gives you this one score for a full batch of data, and Amlan and Jivan had a lot of trouble kind of finding credit assignment for each of the individual samples. So here they designed a different similarity metric between the distributions, which essentially can assign credit to each individual sample in the batch. Okay, I'm not going to give you the details here, but that really made it to work. So the results here are showing two different settings. In the top setting, the structure price kind of good. So we already have more cars and more buildings and so on being placed. While in the bottom, we're going to start with a very bad prior. So there's almost no cars. If you look at the on the left side, there's only like one car on the road, no buildings and so on. And we also wanted to see if the model can learn. And the way we're going to evaluate this model is through a task network. So we generate a full bunch of data. We let MetaSim 2 optimize this data. And then we train a detector on this data and evaluate it on Kitty. And the better your data is, the better the performance should be. And this is basically what happens. So in the first line you have just the probabilistic grammar, which is whatever the prior was, which was not very good. And then as you're training MetaSim, you can see that the performance improves. On the right side, I thought these plots are quite interesting. It's showing a histogram of scenes with different, a distribution of cars in different scenes, from no cars to 15 cars. Some Kitty scenes have 15 cars, and you can compare how the prior against posterior and real distribution look like. So you can see that even with a very bad prior, you can match the histogram quite well. So the model has actually learned pretty well, which I thought was quite fascinating because there was no supervision. Everything is just done by comparing images. So here are some visual results. On the left side, there is samples from this very badly initialized probabilistic grammar. In the middle is scenes optimized with MetaSim. So you can see that it starts putting a lot more houses, a lot more trees, a lot more cars and objects. So it has kind of learned a much better structure. All right, so one more thing I wanted to talk about is objects, right? So this was layout and learning scenes, but we also want to democratize 3D asset creations. So for example, we want people to just take pictures or maybe a video of the object and get 3D models out, right? Because my mom for sure cannot use Maya to create such content. And for VR, that might be very useful, right? And there's been a lot of work now, not just by us, but in the community, of taking images or maybe multiple views and getting 3D models out. And just because there is not a lot of ground truth, so there is not a lot of 3D models aligned with images, there's been a lot of work that tries to do it in an unsupervised fashion. So just from images from the web with very little supervision, maybe just the cameras between different viewpoints, how can we still learn 3D models? Okay, and we're going to discuss this in a little bit. So the typical framework that people exploit is something like this, and this problem is called inverse graphics. So from an image, you want to go back to the graphics parameters. So you take an image, you have a neural net that's going to predict a mesh, lighting, texture, maybe material or whatever. And then since these are graphics properties, you can use a renderer to produce an image, to render an image. And now you can have a loss on the image. You can just compare the input image to the rendered image, L2 loss, whatever you want, right? And if you make this render, graphics renderer differentiable, then this loss can be propagated back to the neural network. Okay, and there's been now a lot of work that create different differentiable renderers. And we have our own at NeurIPS last year, which basically makes a rasterization step differentiable. We call that DBAR. There's a lot of little tricks to make this to work that people don't tell you about in papers. And one is having a loss for the mask that really helps to avoid trivial solutions, as well as having multiple views of the same object. Because then essentially you can impose consistency across viewpoints and make sure that the predictions are consistent. And that really is what makes it to work. So at least in training, you should have multi-view data. All right, so these are some results. These are just on synthetic scenes, the input image in the top left, our predictions, and then we're rendering a 3D texture model here. Looks quite good. I know we tried it, even tried training GANs on this kind of data, where now you want to still produce mesh and texture or whatever, but the loss is on the image, so the discriminator works on the image space and you backprop to the GAN. And you can get pretty decent results as well. Some results on real imagery. And here we follow past work, which essentially takes real imagery, even in training, and annotates key points across different examples. And these key points are used to compute structure from motion camera, which basically gives you different viewpoints of words, and you can use this during your training to impose consistency. This is our result on Pascal, which is very unsatisfying. So essentially cars, we train it on cars. The middle column is our result, and you can see the texture is quite off, and even the shape is not great. And the baseline is also perhaps even worse. And the question is, what's wrong? And one of the things that we thought is because of the data, there's very little data in Pascal, and there's so many different viewpoints of so many different cars, it's just hard to train a good model, okay? And the question we're asking, how can we get better data, such that real data, avoid shape net and so on, such that we can train better models? And yes, you can go to a car show, maybe take videos or whatever, but maybe there's a simpler way, particularly now that we're all stuck at home. And we noticed that the current GANs, style GAN in particular, produces very realistic looking objects. In this case, we're looking at cars. Like, you can almost not tell that this is fake. And messing a little bit with the style GAN code, we kind of get the data we want. So let me tell you what we're doing here. So we found part of the latent code in StyleGAN where you keep where the one part of the code is responsible for viewpoint, and another part is responsible for content. So the actual identity of the object and background and so on. So it turns out that if you keep that content code frozen and only vary viewpoint, you essentially get the same object rendered in different viewpoints. It's not perfect, as if you look at this in detail, you see that it's not perfect, but it's actually pretty damn good. Like, I could be almost convinced this is the same car. And if you keep the viewpoint code fixed and you vary content, you essentially get different cars rendered in the same viewpoint. And this is precisely the data that we need to train a differentiable renderer. Okay, and essentially what we did was something pretty clever. So we're only going to annotate key points on one example, so only on one car, because all the other viewpoints across all the different examples are roughly good. Like, they're roughly matching the viewpoints of the let's say the top car. Okay, so from these key points we get structure from motion camera, and now we're going to assume that For all the other cars that we can render with StyleGAN, we're going to have roughly the same viewpoint. Okay, so all we needed to do is change the learning objective a little bit for training the inverse graphics network, such that it could tolerate a little bit more noise in the camera. So essentially, we make camera latent. We initialize it with the camera estimated from this data, but we let it vary a little bit from that initial camera.
Just a few minutes, so yeah, thank you.
5 minutes?
A bit less, yeah.
Okay, cool. I'll try to finish super soon. So these are our new results. So on the left, input image, and all we change here is just the data. So we have exactly the same network structure and everything, just train it on the StyleGAN data as opposed to Pascal. And you can see that the shapes we get are actually pretty great. And this is comparing it if we train it on StyleGAN data versus if we train it on Pascal. So Pascal is second and fourth row, and StyleGAN data is first and third row. So you can see a drastic difference. And if we just grab some pictures from the web, so the domain is a little bit different than Pascal, you can see the Pascal model like completely fails. So the shapes it produces are just non-reasonable. Whereas this model, which is basically trained on Flickr data, right, through StyleGAN, is doing a really good job here. And this model is quite robust, so you can handle very different types of shapes and textures of these cars, and you get really good, reasonable predictions. So you can imagine that this is basically the workflow, the framework. So you have StyleGAN, it's producing this multi-view data, it's training the inverse graphics network. But now we can be a little bit smarter, and we can take this inverse graphics network and map back to the latent code. And why do you want to do that? Because now suddenly we have a neural renderer, because you can take a mesh, you can take light, you can have texture, and you can now basically go back to the latent code and then use StyleGAN to render that, right? So we kind of get this dual render. One is a graphics render and a neural renderer, which would be StyleGAN here. And we even jointly fine-tuned this entire architecture. Particularly, we wanted to disentangle StyleGAN's code such that mesh would kind of find its own part of the latent code, texture its own latent code, and so on. So we basically trained this with this kind of sparsity induced during training. And then exactly what you do, you get is this dual renderer. So let me just quickly explain what I'm showing here. So on the top is input image. What we use is the inverse graphics network is going to produce the mesh texture and whatever. And in the second row, we just use graphics renderer to render that. And in the last row, we're using this neural renderer. So we can pass this exactly the same 3D properties, map back to the StyleGAN code, and then render back with StyleGAN. And you can see that at the very least, StyleGAN is also able to produce realistic backgrounds and maybe even more realistic cars, because the graphics renderer we use doesn't really model the secondary light effects and so on, right? So there are some limitations in that. And this is, I guess I'm going to stop with this. Now that StyleGAN is kind of disentangled, you can also do some swapping. And what we're gonna do here in different columns is we're gonna first, in the first column, sample for a bunch of different cars, four types of cars. And we're gonna swap either shape of texture or background between them. So essentially, if you look at shape swap column, all the cars should look the same as the car one in the first column. In the third column, all the cars should have roughly the same texture as the second car in the first column. And the last column is just swapping background. So it kind of does a good job. You can still see that the background is not perfectly disentangled. So sometimes the background also changes as you're changing the identity of the car, but most of the time is getting at least the right idea. And do I need to finish here? I guess, right?
That would be great. Thank you.
Okay, cool. I'll just stop here then.
All right. Thank you very much, Simon. Everybody else is muted, but I can hear them clapping
I know.
in my
They're
in my
clapping
mind.
in my head.
Yeah, exactly. Okay, we have time for one quick question. This is a question from Mateus Gadela. He says, originally when you reconstructed the 3D models, you had a mask loss, and you said that that was really important as one of those tricks to get this to work. How does that work with StyleGAM? Because that doesn't have masks.
We just use a segmentation, automatic segmentation. And we basically render like 500,000 images. I don't know how many, 5,000 cars in each view. So even if there was some noise in the mask, it kind of handle it. So yes, we use the mask loss, but it was automatically obtained by mask CNN or something.
Great. Good. Let's everybody in their mind thank Sanya again for her excellent talk.
Yeah, I'll stop sharing.
Super. All right. And I see Aaron. Hey, Aaron.
Hello.
And I'm handing this off to Kalyan, it looks like.
Oh, awesome. All right. Thanks, James. Thanks, Sanya, for that great talk. And so I want to introduce our next speaker. Our next speaker is Adam Hertzman. He's a principal scientist at Adobe Research. And before joining Adobe, he was actually faculty at the University of Toronto. So we have, like, I guess, 2 speakers with U of T connections here. He's also an ACM and IEEE fellow. And for his seminal work across graphics, vision, machine learning, and HCI, he's worked across many topics in the space, including image synthesis, non-photorealistic rendering, human motion modeling, computational photography, graphic design. So it's surely a great person to have for this workshop. And recently, he's been studying content creation with deep neural networks. So this is a great opportunity for us to hear his thoughts on this in this space. So take it away, Adam, and thank you.
Great. Thanks for having me. I hope you can see my slides. This is going to be more of a high-level discussion about the culture of our different communities rather than a technical talk. And the starting point here is that there's a lot of papers now in image synthesis in the vision conferences, CVPR, AICCW. There's a lot of really nice stuff. And in some sense, some of the most exciting stuff in the field. And we've seen a lot of stuff that I left out that was earlier today, and I don't have room for everything in the slide. And this isn't just a fringe phenomenon. Some of the award-winning papers or nominees are essentially computer graphics papers, including the Mara Prize winner from ICCW, essentially a computer graphics paper, image synthesis. And so I've always thought of SIGGRAPH as the most exciting place to publish my graphics work. It's really the place I think a lot of people have seen as this is where you publish stuff like this. But this year, there's 124 graphics papers at SIGGRAPH 2020, whereas at CVPR this year, there are 93 that declare their primary subject area as image and video synthesis, 29 as neural generative models, and so on. So it seems like, in some sense, there are more graphics papers happening at CVPR than at SIGGRAPH, which is like a really strange turn of events in some ways. And I shared my talk title with some colleagues on Facebook, and the first response was, oh man, CVPR is absolutely a graphics conference. The second response was, it does stand for computer vision and painting and rasterization, right? So I feel like this is something worth talking about, discussing, a little bit. What does this mean? How do these fields differ? How do these venues differ? And I want to say just a little bit about what I see as being kind of blind spots in vision publication and reviewing. And I know a lot of people, I'm sure, attending, and certainly a lot of the speakers have experience with SIGGRAPH, and I view a lot of these comments maybe for people who don't have experience with SIGGRAPH or the graphics venues and have really come from a pure vision background. So I would first start off by talking about how things got this way, and sort of one factor I think is certainly the publication styles of these venues are different. And in SIGGRAPH, it kind of feels like every paper you write, you're constructing this beautiful masterpiece, getting everything just right with artistically constructed, single origin, shade grown, everything is perfect. Whereas computer vision often feels like this massive, stampede where you're just rushing to get that damn paper out the door as fast as possible before you get scooped by 15 archive competitors. So there are a lot of pros and cons to these different kinds of approaches, but one thing we've seen is the pace of progress in computer vision recently has been just staggeringly fast. But there has been a long history of generative models in vision, and we saw in this morning talks that used the notion of analysis by synthesis. We saw a lot of computer graphics models in the construction of these different representations. And generally, there has been at times expressed this belief that building vision systems requires understanding the image formation process. One area where this has, I think, been strong, has been in the notion of texture modeling. I think a lot of the significant work in texture discrimination has had a part of the paper where they randomly sample from the model, generate texture in order to understand and validate and just test out their texture discrimination model. And this has led to papers in Vision on texture synthesis, the graphics problem. So this is the work by Efros and Lung in '99, which is really nice work in creating textures from examples in similar spirit. And just to briefly mention my own work, this led to my own work at SIGGRAPH on style transfer, generating texture paintings from a single example of that style, or conditional layout of scenes based on texture from an example. And there was also a similar paper from Efros and Freeman in the same session. So to talk about what this means, we think of computer graphics as being SIGGRAPH as being about computer graphics and interactive techniques. Computer vision is about computer vision. But those sort of short descriptions are actually incomplete. I don't think that's really what these conferences are about. So let's look at SIGGRAPH, for example. About 30 years ago or more, basically people thought computer graphics and SIGGRAPH were about realistic rendering and animation, geometric modeling. But most of the papers that people thought of as being computer graphics were really about rendering. But by the time I started attending SIGGRAPH, there has been this explosion of topics, of things that people had not thought of graphics 10 years before, of image-based rendering and generating cartoons and modeling, modifying videos and haptic tangible interfaces and VR storytelling. And even today, looking at this year's SIGGRAPH papers that are coming out soon, there's just this incredible diversity of interesting ideas and new things that people had not even thought to publish on the previous year. And I think, and I'm very excited about this coming program. And I think part of the success of SIGGRAPH has been from this really openness to new problem statements and new ideas that were not what had been previously been considered computer graphics. And so I would argue that really the topic of the conference is not computer graphics interactive techniques or computer vision, it's what interests the community. So as another example, SIGGRAPH has now has a lot of publications on computational fabrication and computer-aided design of essentially physical structures. And this is not something that was considered computer graphics 20 years ago, but it's something that's really appropriately fits the kind of interests and skills that the computer graphics community has. One way this sort of had manifested in the past was if a reviewer wrote, "I haven't seen that problem before," at SIGGRAPH that means, "Oh, I'm excited, probably accept the paper." Whereas it used to be envisioned that meant reject. That vision reviewers used to say, this problem has been worked on in vision before, probably not computer vision. And that seems like that's really changed, and this is really one positive thing for the vision community. But to think about what the community likes, I think it's perhaps also interesting to think about who are the people attending. And I have this stereotype, I don't know if this is how accurate this is, but I have this impression that a lot of vision people, certainly of the older generation of vision researchers, got inspired by vision, by the book Vision by David Marr, by Gerald Escher-Bach, by seeing science fiction versions of AIs, and they wanted to build psychopathic space AIs. So they're really motivated by the idea of modeling and understanding intelligence. For a lot of us computer graphics people, we started out being interested in art. So for me, I made animations when I was a kid. I watched a lot of animation, went to experimental animation festivals and movies at Pixar and so on. I studied art in college. I did a lot of painting. And I think everyone's different and different people have sort of different backgrounds, but a lot of graphics people really start from a place of wanting to create and enable art. And so there's these sort of two stereotypical viewpoints, I think. From the AI and vision point of view, creating images and creating art are really kinds of intelligence that we want to model. So we take whatever tools we have for modeling intelligence, and we just apply that to art. And in the extreme sort of caricature of that, it's like we take all of our art, feed it into our supervised model, and then we can make more art. And the graphics viewpoint starts from a really different point of view, that algorithms and software are tools for art and expression. And a lot of this comes from the SIGGRAPH community's interaction with games and visual effects community, as well as the fact that a lot of people in graphics have some kind of art background or some connection with the arts. And all of these fields is this very strong experience that that these pieces of software are ultimately things that people use to create art or to express themselves or communicate with each other. And so what this means, to some extent, is that the CVPR publication process cares about automation and it cares about quantitative evaluation, whereas SIGGRAPH cares a lot more about user control and the visual qualities of the results. And so, one sort of extreme example of this is that at CVPR, if your paper has some user steps where the user specifies a few things as input, that can hurt you with the reviewers. Whereas with SIGGRAPH, if your method is completely automatic and has no user control whatsoever, that can hurt you with the reviewers. So it's like there's very different emphasis in the interest here. And I want to emphasize, I don't think there's any right or wrong to these points of view. All these different approaches have a lot of value. And another factor I think that CVPR has made such good strides here is that SIGGRAPH has not really embraced machine learning methods until recently. And this is something I've spoken, written about before as well. I have had no problem publishing machine learning work at SIGGRAPH, but I think that and I think because SIGGRAPH is so open to different ideas, but a lot of graphics researchers have been resistant or reticent about adopting these techniques. And even 5 years ago, I was hearing people say, oh, this deep learning stuff, it's just a fad. I don't really know that it really works. And so this is why SIGGRAPH has not been the innovator that CVPR has. There's a few things, though, I think it's worth pointing out that CVPR has not been as good at when it comes to image synthesis techniques. These are things around focusing on the aesthetics and the visual quality of the work. But I can mention the paper by Gaddis et al., Neural Style Transfer, and I feel comfortable saying a few skeptical things about it because it's clearly such an important paper, seminal work, very, very important. However, like the visual results, and some of them, honestly, I don't think they look that good. They're an advance in the state of the art, but they don't really a lot of times capture the visual style of the artwork that they're starting from, which is fine in a research paper. It's an advance, but these are things worth discussing. And I feel like there's been a lot of follow-up work that has basically just treated it as like, okay, now you just do the same thing, but with slightly faster or few shot or something. And there's not really like people paying attention to what are the qualities that these artworks have and how do we model those. Human motion is another place where historically CVPR's vision research has not been so good at looking at the images themselves. And so we've had, this has changed I think a bit recently, but we've had a lot of these papers that have these MATLAB bone structure visualizations of motions, and there's no skinned model, there's no ground plane, there's no cast shadows, and you just cannot tell from these images if the motions look any good. In contrast, I would point to, for example, some of the early work of David Salison's group and his students at UW, and then when those students became professors. These papers are really great models for how do you qualitatively discuss the visual phenomenon going on in a particular scene. For example, in this hatching illustration from their work, you break apart what are the things that make this visual phenomenon what it is, and then create systems that capture these visual phenomena. There's no quantitative evaluation in this paper, there's no numbers, but this result here, I mean, I think, obviously this is a beautiful picture they were able to render, and you can see if you go through the paper how it captured the goals that they set out to achieve. Similarly, in character animation, we spend a lot of time looking at the motions and comparing them to the real phenomenon. So this is some work that we did where we spent a lot of time comparing, like, do the footfalls happen in the same way for the characters as they do for the real person? Because those are really perceptually salient to how we view the motion. We also spend a lot of time understanding the physics and dynamics and how dancers think about these things when trying to model these different phenomena in the world. And I feel like in the vision learning world, there can be a little bit of a monomania around just a focus on learning. So this is a video from a work that my students did a long time ago. And the video is probably playing very choppily, but it's not very important. But basically, they built a physics-based character controller based on elegant high-level principles from biomechanics and robotics, and were able to demonstrate all of these different capabilities it had. And I gave talks on this work at some learning venues like CFAR and Snowbird. And each time I presented it, there'd be some person in the talk, in the audience, who'd say, ask me about the training data or which step was before or after learning. And these questions, they flabbergasted me because there's no learning whatsoever in this work. And it never mentioned learning or training data in the talk, and somehow it's just assumed that there must be. But my point is that you can do a lot of really valuable work that doesn't involve machine learning. I know this seems really shocking. That being said, I think the best work combines this kind of modeling with machine learning. And so, for example, I see there's a paper at SIGGRAPH coming up from Michael Van de Pan and others that use the kinds of low-dimensional representations we had in this paper together with reinforcement learning. One other point I want to make is that the emphasis on quantitative evaluation can be dangerous. Quantitative evaluation is a really valuable thing, and it's really been important for the field to move forward with the Middlebury data sets and ImageNet. But it can also be dangerous if all we care about are focusing on numbers. And I feel like I see this as an IC and so on, that vision reviewers can be overly obsessed with quantitative evaluation, even when that evaluation is not meaningful. It feels like you read a paper, you got to have a table of numbers, and there's not necessarily a lot of thought into whether those numbers really are an important part of making the convincing case in the paper that you have a good idea. And sometimes those evaluations are actually not very well performed and not very well constructed. And I have some references on the slide for some discussions of that topic in other venues, but I think a lot of that applies for vision as well. One positive note here is that I think a lot of the interesting work happening in the vision venues is coming from graphics researchers. And so there's really nice sort of melding of cultures of people coming to bringing ideas from different places together. And a lot of the interesting work going on, you see maybe one of the authors has a lot of experience with SIGGRAPH, or even they come from a graphics lab. And I think that kind of shows in the quality of the results. In particular, I'd point to Jaakko Lettinen's lab at NVIDIA. They developed StyleGAN, Progressive GAN, a lot of great work in this area. All of these people, as far as I know, have PhDs in computer graphics. They did their theses on ray tracing and rendering stuff, and now they're doing all this great work in GANs. And they will tell you that they have been successful in making really great GAN techniques because of their experience in graphics and their focus on the visual quality of the results and their attention to the visual details and how things look. I just briefly plug some of my own work in this space. We have a paper coming up on Wednesday for line drawing of 3D meshes. And this is a place where we have combined ideas from the recent image translation works, Pix2Pix, as well as more older techniques from computer graphics, just to get the best of both worlds. And I feel like a lot of my best research ideas these days are taking older ideas from computer graphics research and combining them with new ideas in machine learning and deep learning. I also want to briefly plug our GAN-based work, which is online on arXiv and YouTube. Here we're able to learn interesting directions within a pre-trained GAN without any supervision whatsoever. So you give us a GAN you've trained, and we will tell you essentially what are the interesting directions that this model has learned. And the nice thing about this is a super simple method, easy to implement, which I think is an advantage. And it's also something where there's no, I don't think there's any meaningful quantitative evaluation we can do. I think you read this paper, you watch the video, you get a sense for what it does. And we could throw in a pro forma quantitative evaluation because you got to have some numbers in your paper, but I just don't see what value it would actually have. I've maybe made a few points here, but I would say that my message, I feel like both these approaches have their strengths and their weaknesses between kind of the way people do things at CVPR and at SIGGRAPH. But if CVPR is going to be a place that publishes graphics papers, that is becoming like a first tier venue for graphics, which seems like it's a bizarre situation, then I think it should be open to this work, which is more focused on visual quality. And I would encourage people who want to work in the space to adopt this mindset, read more SIGGRAPH papers, and think more about how do the images look and not just what are the scores that you're getting. Thank you.
Thank you. Liang, you're on mute.
Yeah, thank you, Alan. That was great. Yeah, thank you. So a couple of questions from the audience. So Arslan Basharat is asking, are there lessons learned on best practices for quantification from other fields that you are aware of and that you might recommend for the vision community to follow?
Yes. So I think there's a lot of issues, and the short version is it's complicated. In that paper by Greenberg and Buxton, I think, where they're specifically talking about quantification in HCI, is a really nice sort of argument that in different types of times in the design and research process, you want different kinds of evaluation. I think, so the first question is, what exactly is the point of your study? What are you trying to prove? There's a lot of very specific things about the way that you run user studies that are important. Like you should randomize your stimuli and make sure that the people can't tell which ones are from your work versus the other work, and so on. There's also there's a lot of work, a lot of study of the replication crisis in psychology and other fields, where you have to have p less than 0.05 to publish a paper, and then people have essentially learned, intentionally or unintentionally, how to completely hack that and publish reproducible work, but always getting that score. So I would say, the short answer is kind of, look at some of those other venues, because it's pretty complicated.
Mm-hmm. I think just kind of along those same lines, Animesh Karnevar is saying that getting qualitative assessments, for example, from Mechanical Turks is not always possible, maybe because of budgets. However, if we wish to pronounce the focus on perceptive qualitative results, there's always the risk of cherry picking results. So how do you propose, like, a middle ground between like quantitative and qualitative evaluations?
Well, I guess I would sort of see, I don't think, again, like, I don't know there's a simple answer, but I would sort of say that there's, I think of there being kind of two regimes or two extremes. One extreme is we present a simple method that takes an input, produces an output, and you can understand from the algorithm when it's going to work and when it's not going to work. And we show a bunch of cases where it works really well. And from that, you can sometimes as a reader, you can be pretty convinced that they've done a good job, and the authors have sort of clearly communicated when it works, it doesn't work. And maybe you're willing to trust the authors in some cases. In other cases, like if the claim is this is going to work on every image or work on 80% of images, or the advantage over the previous work is much more subtle, and it's really more like, well, in this case, it kind of makes more sense. It might work better, it might not. Then it seems like you really need to do a much more rigorous, thorough evaluation and be able to make the case that your scores are actually meaningful.
And Alyosha has a question. Most of my students are obsessed with FID because they want a number. Do you have any advice for them?
I mean, yeah, I think there's three things. Either we improve the culture of the field, or we improve our evaluation metrics, or I've been told that a FID is better FID like kind of means that you're doing a little bit better, but I don't know. I don't know if there's a good answer for that.
Actually, I had a question. I mean, I guess you're suggesting that some of the ways in vision we evaluate our work is not great, but you also said that some of the nicest work in like graphics topics is now happening in CVPR and not in the graphics conferences. So like, how do you kind of put those two together?
Well, I think people who are doing well in these areas have figured out how to do a good job at both, of like making beautiful images and also reporting good FID scores.
Mm-hmm. I think we have a few more questions. So Mingyu is actually asking, do you think it's a good idea for CVPR to accept art papers?
I guess it depends what you mean by an art paper. I mean, I would say if you mean art paper by like, here's my artwork that I did, I don't think it makes any sense for that to be in the technical track, because we don't know, CVPR doesn't know how to evaluate those kinds of papers, and it's such a different culture. I think papers that are computer vision or computer graphics tools for artistic tools are potentially useful. I mean, I'm not sure if I'm answering the right question.
Okay. And David Scott Hayden's asking, in discussing the strengths of SIGGRAPH, you emphasize strengths being a focus on visual quality and also intelligent example physics-based modeling. So how do you weight the importance of these two things? So visual quality and physics-based modeling.
I don't think I can weigh these things and say that one is more important than the other. It depends on the, on the topic. I think that I would say like even in our work on physics-based modeling and character animation, we are building these physical models with a goal to produce results that are visually accurate. And we believe that we will make more perceptually appealing or accurate results by modeling the physics in certain ways. And we're going to ignore parts of the physics that don't seem salient to the visual quality of the results.
Okay. I think that basically wraps up the Q&A session. If other folks have more questions, maybe you can post them. Aaron, I don't know if you have a little time, maybe you can answer them in the Zoom chat window. So with that, maybe we'll thank Aaron virtually for his great talk and the Q&A again. And that actually wraps up this segment of this session. We'll have a short break now and be back in 20 minutes, right, Mingyu? I think back at 3:15 Pacific for Ying's talk. So 20-minute break. We'll see you guys in 20 minutes. Thanks.
See you guys later. Hey, Yin, I think you are on mute now. Can you type?
Yeah.
Cool.
It's working?
I can hear you clearly.
Okay.
Weilong, you are on mute now.
Sounds good. So we're gonna start at the 3:15.
3:15?
Yeah, it's like 1 minute. We're gonna start in 1 minute.
Oh, okay.
You probably wanna start a screen share. There's the big green button in the middle.
I can share now?
Yes,
Okay.
great.
Nothing else?
That looks good. You probably wanna hit the
Good.
present. Yeah.
Okay. What about this one? Do I need to minimize it? Like this?
I think this is look good. Shall I get started? All right. So everyone, welcome to our last invited speaker session, and our next speaker is In. In received a PhD degree in computer science from City University of Hong Kong, and his research interest is in data-driven graphics design, for example, web page design, magazine design, with the goal of teaching machines to learn to design from data. Let's welcome In.
Okay. So in this talk, I will introduce emerging research direction called data-driven graphic design, which aims to bring AI into a graphic design world. So graphic design is a common visual medium and one of the most powerful tools to affect people's behavior. We are surrounded and affected by graphic designs every day, for example, on a street or in a subway. At the core of the graphic design is information communication through the combination of symbols, images, and text. We can model the information communication process using autoencoder. With some message in mind, designers try to encode the message into a graphic design, for example, a music poster here. And when audiences see the poster, they try to decode the message underlying it. And the ultimate goal of graphic design is to minimize the difference between the ground truth message and the message decoded by the audiences. However, creating a good graphic design is very challenging as it involves thousands of decisions on various factors. For example, the images, fonts, colors, and layouts. But why graphic designers need to put so much consideration into just creating a single page with a few elements? The main reason is that a good graphic design is more than just being visually attractive. It needs to achieve several challenging goals. Now I will use an example to illustrate how these goals are realized in practice. And first of all the graphic designs need to conform to some visual design principles. For example, visual balance, alignment, and symmetry. In this poster, the sun at the upper left corner and the hill at the bottom right corner will put visual weight at the center of this design. This will make the entire design look more visually stable. And also, a good graphic design needs to be eye-catching and memorable so that it can stand out from its context. And this poster used the curved wave shape and large color difference between the foreground and background to create a high contrast effect. And this will immediately catch people's eyes. And a good graphic design also needs to build the right personalities. Personality here refers to the overall look and feel of a graphic design, which can give you instant impression even before you start reading the contents. In this poster, the boat floating at the tip of the wave and chased by a group of bizarre fishes will signify an exciting adventure. And also the irregular composition makes the entire design very creative. So this poster will feel exciting and creative. And also a good graphic design should be able to direct our eyes to travel through the design smoothly so that we can quickly get the information we want. When looking at this poster, our eyes will start with the boat, then move to the fishes, and finally to the important region containing the time and avenue of the music event. And finally, every graphic design has its own underlying message to deliver. And by looking at visual and textual elements on this poster, we can basically understand what it wants to tell us. Like to say, there will be a cool music festival. And more importantly, and a good graphic design needs to achieve all the goals in very limited time and space. And so given the difficulty of creating graphic designs, we asked the question that if it's possible to train computers to design. Meanwhile, massive amounts of graphic design data online provides an opportunity to understand and replicate a graphic design process. Thus, our question becomes, if it's possible to make use of such large-scale data to train computers to design. Enabling computers to understand and generate graphic designs has many practical applications. One direct application is to enable more intelligent features in existing content creation tools to augment human. Another possible application is for online advertising. A critical problem in online advertising is personalization at scale. So as we are expanding the users that we are creating contents for, we will be facing two fundamental problems. The first one is how to create variations of the content, while the second one is how to create an imagery of the content. While the first problem has been widely explored with a lot of works on recommender systems, the research efforts on the second problem are still quite limited, and the techniques used in industry are mainly based on templates or simple heuristics. So we believe data-driven graphic design techniques will have a potential to revolutionize online advertising field. Some efforts have been made on using data to help graphic design, and the progress is happening in both academia and the industry. In academic world, early works mainly focus on learning visual aesthetic and style models, while later works start to explore other fundamental problems. For example, how to direct people's attention and how to catch people's eyes and how to build design personalities. In industry, several commercial products have emerged recently in an attempt to bring intelligence into graphic design creation. However, they are still easy to use tools without much built-in intelligence. And this is partly because that research works on this direction are still quite rare. And now I will use several of our recent works to demonstrate how we can bring AI into graphic design. So the first work I'm going to talk about is on how to train computers to understand personalities of graphic designs. Given this poster, what you feel of it? I feel it's cute. The goal of this work is to understand what makes a graphic design have a certain personality. In this heat map and the red colors highlight the regions that are important to making the poster cute. Our basic idea is to learn a personality scaling function, which takes as input a graphic design and a personality label and outputs a scale that measures the degree of the design having the personality. To find if a region is important for a personality, and we just block the region and observe how the predicted scale will change. If the scale goes down significantly, that means this region is important. Otherwise, if the scale doesn't change too much, it means this region is not important. Since annotating design personalities can be both ambiguous and expensive, we seek to leverage web data to learn our scaling function. So one naive solution is to treat personality labels as query keywords, and then we can train a classifier by using the keywords as hard labels. And finally, we can use the confidence scales of the classifier as our scaling function. However, the hard labels cannot represent varying degrees of personalities. For example, these two posters are returned as cute, but their cuteness can be at different levels. And further, a single graphic design may have multiple personalities at the same time. For example, this poster can be both cute and elegant with almost the same degree. And this will confuse the learning of the classifier. So our idea is that we learn a regression function instead by using the pairwise comparisons generated from web data. Our intuition here is that although we cannot ensure designs labeled as cute are 100% cute, it's safe to assume designs labeled as cute are more cute than designs labeled as elegant. With the synthetic data, we learn our scaling function by ranking design pairs based on their personality labels. And inputs to our framework include a personality label and the positive design containing the label and the negative design that doesn't contain the label. Then we use our scaling function to map the two designs to their personality scales. Finally, our network is trained by requiring the positive scale to be larger than the negative scale. So our learned scaling function can be used to tell what's important for a personality. And here I show some examples for artistic and romantic. For each personality, I show two posters and along with their heat maps, as well as some discriminative patches mined from our dataset. So as we can see that artistic posters tend to use more decorative patterns, while the romantic posters tend to make intensive use of interaction between man and woman. And our scaling function can also be used to suggest some properties for basic elements. For example, we can suggest proper image cropping to make a design look more creative. And for comparison, we also saw a result manually created by a novice. And we can also automatically enhance a photo to make a design look more fresh. We can also suggest the font faces to make a design look more elegant or energetic. And finally, we can also suggest the font colors to make a poster more cute or vintage. And since our network learns a personality-aware feature representation, we can use it to transfer personalities between designs. For example, given a tag design and a source design, we can modify the source design to match the personality of the tag design. In this example, and to mimic the personality of the tag design. And in the source design, the font faces and colors are modified, and the background image is enhanced properly. And here is another result. And in this example, to match the personality of the tag design, the arrangement of objects in the source design is modified. And the second work I'm going to talk about is how to lay out to better present contents. Graphic designers often determine the way to lay out based on contents to present. For example, all the 4 magazine pages belong to the same fashion category, but they have different layouts because of different contents. And the first 2 pages are about interviews, having a large hero photos. The third page is about brief biographies of multiple persons, with a layout that has multiple columns. And the last page is about introduction to several region fashion trends, and is arranged in a more creative and irregular way. The goal of this work is to learn a content-aware generative model for graphic design layouts, which will capture the effect of input contents on layouts. Our model learns a distribution of graphic design layouts conditioned on input contents. To represent input contents of a graphic design, we use its images, the keywords of its text, and also some design attributes. We use an embedding network to encode the input contents into content features. And then we use a layout generative network to generate layouts based on the content features. We also introduce a layout encoder, which will map input layout into a latent code. And this will allow us to control the layout generation process by inferring a latent vector from some input signal. To train our network, and we construct a magazine layout dataset, which contains a large set of magazine pages. For each page, we annotate its layout, its images, and keywords, and also category. Once trained, our network can be used for automatic layout generation. So to do this, and we sample a latent vector from a prior distribution, and then we feed the latent vector along with the input contents into our generator. And we can also introduce some constraints into layout generation. For example, given input contents and a parcel layout, we can generate a complete layout that conforms to the parcel inputs. And to do this, and we use our layout encoder to map the parcel input into a latent vector, and then we feed the vector and the input contents into our generator. And here I show some results for automatic layout generation. And we compare with 2 baselines that's based on retrieval. And first baseline use the content features with pre-trained weights, and second baseline use fine-tuned features with fine-tuned features by our training. And we can see that the 2 baseline either generate a very large image with too much text on it, or it give too little space to the image, while our layout is more similar to the ground truth. And here are some results for constrained layout generation. We compare with a retrieval-based baseline that considers both content and layout similarity. And we can see that our results, our method can generate a layout that better matches the parcel layout and also is closer to the ground truth. We also compare with existing rule-based methods. So it's interesting to know that although our method is purely data-driven, it can generate layouts that will follow some visual design guidelines. For example, the symmetry and the alignment. And further, the existing method is not aware of input contents. That to say, they will give the same outputs regardless of input contents. In contrast, our method can generate a different layout when the input image is changed. And finally, we investigate the effect of input contents on generated layouts. In this figure, and each row is generated by using the same image, and each column is generated by using the same set of keywords. For the first column, as we change the photo from a house to a couple, the layout is changed from a more text-heavy to a larger image followed by some sparse text. And as we change the input keywords from a food description to a place introduction, the images are moved towards the page center. And this will place the images into more central rows, and that will give readers a stunning first impression of the place to be introduced. So then I will discuss some open problems that we are working on, and also maybe of interest to computer vision community. The first problem is if we can learn end-to-end generative models for graphic designs. There are several challenges to realizing this goal. The first challenge is that, as compared with natural images, graphic designs often have highly varied appearance and structure, and this makes it quite challenging to directly capture such complex data distribution. The second challenge is that, as discussed before, a good graphic design has to satisfy multiple criteria, both visual and functional, and this will bring additional challenge to loose formulation. And to approach the first challenge, we will explore if it's possible to make some assumption to make the problem more tractable. So we found that many existing deep generative networks are assumed to be category specific. Since the objects in the same category are similar, this will greatly reduce the space of appearance and structure to model. We can view this as modeling conditional distribution given the input variable y. For natural objects and scenes, y here can be straightforwardly defined as semantic categories, for example, face and chair. But what is y for graphic design is not well defined. Since graphic designs, as mentioned before, are created to achieve some high-level goals, a straightforward solution is to use a variable that describes these goals. For example, the category, topic, feeling, message, and target audience. However, how many factors and what factors to use as inputs is still an open question. Too few factors will make the problem under constraint, and too many factors will dramatically increase the amount of training data needed. The second problem is what rules to use. A naive choice is a reconstruction rules that measures the difference between generated designs and the ground truth. However, graphic design generation is uncertain. To see this, I show example from a design crowdsourcing platform where designers are given a brief description of the requirement from a customer and upload their created designs. As we can see from this example, although given the same inputs, the different designers tend to produce quite different designs. Another choice is to use the gut rules. The success of these rules relies on the performance of the discriminator. Like to say, how well the discriminator can determine the realism of input contents. For natural images, since they are just 2D projections of our world, their realism can be characterized by some local visual patterns. For example, the grass are mostly green, and the houses are on the ground, and these patterns can be well recognized by convolutional neural networks. However, for graphic designs, what makes a graphic design real is not well defined. The realism can be determined by both visual quality and functional effectiveness. While the former can be well captured by existing models, the latter will be very challenging to learn from scratch using raw visual inputs. We believe that defining a good rules calls for the development of more powerful models for understanding functionality of the graphic design. For example, for predicting visual saliency, personalities, or even the underlying messages of graphic designs. The second problem is called cross-word knowledge transfer. For other projects that I have discussed before, what we do is we learn some knowledge from graphic design data and apply it back to graphic design problems. So an interesting question to ask here is whether it's possible to learn some knowledge from graphic design domain, but apply it to some real-world problems. To answer this question, we need to explore what knowledge to transfer. We believe the first type of knowledge is human heuristics. Graphic designers often use many heuristics to get their design decisions. Some of the heuristics are well-known rules that can be found in standard textbooks or learned at design schools. Other heuristics may be inferred from past experimentation or careful study of existing examples. And they may be frequently used by designers, but just too complex and subtle to write down. The problem here is how to learn such latent heuristics and apply them to problems beyond graphic design domain. So for example, we can learn the heuristics for how to adjust photo colors and how to frame photos in graphic designs. Then we can apply the learned knowledge to existing image recoloring and cropping problems. The second type of knowledge is human creativity. We believe that modeling human creativity will be important to AI systems for content creation in the future, because we will finally be interested in not only reproducing highly realistic images, but also creating some novel forms that have never been seen before. So the problem here is how to learn such creativity from graphic design data and apply it to some different content creation tasks. So to quickly summarize my talk, the data-driven graphic design is a high impact but under research direction. And it has many promising commercial values. And I also use some example to demonstrate how we can help graphic design with machine intelligence. And finally, I also discuss that there are still many interesting and challenging problems to explore in the future along this direction. So this is the end of my talk. Thanks.
Great. Thank you, Ying, for the great talk. We might not have time for the live questions, but Ying will stay around to answer the question on the chat. And thank you very much, Ying.
Okay, thank you.
So now I'm going to introduce the next speaker and also our last invited speaker, Mingxuan. Mingxuan, have you been?
Yes.
Okay.
I can hear you.
Great. Mingxuan is the professor in EE and CS at the University of California, Merced, and he's also a research scientist at Google and a fellow of IEEE. Mingxuan have done many impactful work on object tracking, image segmentation, slide transfer, generative models, and let's welcome Mingxuan.
Thank you.
Yeah.
Thanks for inviting me to this workshop. So today I'm going to talk about our recent work on image synthesis and style transfer. So can you see my slides?
Yes.
Okay, and I'll turn off video. I guess this probably saved the traffic. All right, so okay. Okay, so So today I'm going to talk about our recent work on image synthesis and video synthesis. And in terms of image, I will talk about style transfer, image translation, and some synthesis work. And for video, I will talk about similar things, and also, if time allows, I'll talk about frame interpolation. So, this is the work that we did back in 2017. So the idea is to train a network so that we can transfer 1,000 style in one network and with diverse output. And so we turn the problem of style transfer as textual synthesis, and then with content that we will be able to generate new contents and with diverse outputs. And so, and we also extend that for video, but this one we extend that with some post-processing, so that you later on I will show you one work that we can operate. We can transfer video contents without post-processing steps. And so that is based on, so the first work that we did was based on 1,000 pre-selected style. And the next work we did was basically we continue to develop methods that work on any style without pre-training. So the idea is pretty simple. Basically, rip apart encoder and decoder and add in some transform, and so that we add in content and style into that. And the transform we use are very standard, are from signal processing. One is whitening, the other is coloring. And with our method, then we will be able to generate style transfer result without any training. And it's also fun to see that we reuse the good old icon vector. And we have been using that for many other things. And it's also good to know that we can reuse that for style transfer. And the next thing we did, but for the previous two work are basically for for artistic style transfer, and the contents are distorted. So next work we did was to see whether we can generate photorealistic style transfer result or not. And so in that, so basically we add two more modules into that so that we can correct the contents, so that this can be generated without pre-training and the result are photorealistic. And so along the way, we find out that we can pose style transfer as linear transformation between content and the desired style output. So the next thing we did was basically we developed one method just based on linear transforms. And for that, we can use the same network for many things, for artistic style transfer, for photorealistic style transfer, and without any post-processing, we still can get a very smooth results. And this runs in real time in terms of GPU, about 140 frames on GPU, and that was last year. And all the code are available on our website. So the next work we did was basically to learn how to draw, how to transfer pencil style, so that I suppose, I assume that Aaron Hertzman might have talked about this during his talk, but basically we learned to draw with different hand strokes and with different shading, so that we would, and this turned out to be a difficult problem, as we need to take shading into account. And so that, so basically we in the end, we have three stroke and two shading style that we can combine with, so that we can generate different results. And so for the previous work, that only worked for high resolution, about 1K by 1K images. And and one person asked us whether we can apply the same method for HDTV or not. And it turns out that we could not, because of memory issue. So we've come up with ways to distill networks so that we can take encoder and decoder into account, and so that we can find, and we add in one linear embedding so that we can reduce the number of filters in the encoder and decoder, so that we can generate star transfer with high ultra resolution 5K by 5K, and we still can fit into the GPUs. And this is work that we are going to present this year at CVPR. And we also work on image translation, and I think Mingyu and others might have talked about this before, so I don't need to get into this. But basically, this was the work that we developed we presented in AICCW 18. So the idea is to generate more diverse translation results, and so that and there are several ways that we can generate diverse outputs. We can use latent space, or we can use reference image, and so that we can generate not just one output but multiple outputs. And later on, I also discuss some of our recent work on how to do morphing with more diverse output, and also with attributes. Okay. Oh yeah, and we extend that to multi-domain instead of two domain at a time. And this is similar to StarGround. Okay. And along the way, we find out one of the problems in image translation is more collapse, and we find a way to force the network to seek the modes in distribution in synthesizer result, and that allows us to generate more diverse output easily. And there is also one work in iClear in 2019 by Honglek, and both ideas are concurrent work, just like Mnut and Drit. So, and we also work on video synthesis. So this work is about how to synthesize. When we hear music, then we will immediately relate some dance moves. So the question is that whether we can learn from some dance movement, and then we can compose them into new ones. And so this is a pretty difficult problem, because it's a multimodal, and we have to account for we have to synchronize both music and motion. So the approach we take is to approach this problem by analysis. So we decompose this work into several basic units, and then we find out how they transit, and then so that it allows us to compose them together. And so then we can compose, once we find all the dance music, and we can synchronize music beats, and then we can synthesize different dance movements. From different choreographies. So we start with mocap data, and later, and we add in some synthesizer from Dingzhen's work, Dingzhen and Ming's work, so that we can translate the mocap data into real data. And I believe Mingyu has a better video than this one, but. Okay, so, and so in addition to that, we also develop method to edit image content. So for example, here, what you see here, we want to insert object into this segment image. So, so you may ask why we work on segmentation result, but basically this is easier for us to analyze that, and then from this we can also use pix to pix to fresh out the contents. So if you see, so for this type of problems, we need to figure out the contents, and we also need to figure out the object interactions. So in our work, we cover more about object interaction, but for this one, we need to figure out the context so that we can insert object at the right place and right size. So for this image here, all of them are synthesized except one of them is true. So only this one is true. All the other are synthesized. And likewise here, you probably can, there is one image that we insert. And so this is the insert. Although we do not do branding, so you probably can see that it's still, there are still some artifacts. You probably can spot that. But we should be able to get better result with some branding process. And here we take one video and then one video of this guy and try to insert into another video. And likewise, we take this car and insert into this video. And so because our background, so we would not be able to just take that, just insert into another video without any noticeable artifacts. So we find there are some way that we can insert object with fewer artifacts this way. And here we do not take ground point into account. So basically we just assume that it's flat or the moving, the background are similar. Okay, and we also work on 3D affordance. So basically, as I mentioned, so basically the idea is that given an image like this, how do we insert an object into a right place with right pose? And we also need to figure out where we can put this person and where this person can sit or stand and in 3D. So basically, from one single image, we need to figure out a 3D configuration. And we also need to know the object inside so that we can put the right person in the right place. Otherwise, it's rare to see a person standing on top of a bay, although some do, but it's less frequently. And we also need to figure out where the person can sit and so on and so forth. Okay, and so this is also a joint work with when I was at NVIDIA with colleague there. So the idea is that given a short video, then how do we figure out the optical flow and interpret the contents and synthesize that? And so this is super slow-mo, and this the source code is also available online. Well, not from us, but from someone else. We implement that and make it available on GitHub. And so this is super slow-mo. And another thing we find out is that simply by figuring out depth information in a scene, that allows us to better estimate optic flow and better interpret the result. So the main idea here is that just to figure out depth and use that to interpret flow and to estimate more reliable optical flow, and so that we can synthesize better contents. And this is another work that we presented last year. So basically, instead of using linear optical flow model, we use quadratic function to estimate object motion. And then so basically, when you have a nonlinear motion, then this method performs better. I can show you. Okay. So basically, when you have large and nonlinear motion, this type of method performs better than conventional ones. Okay, and okay, so that's I went back quickly and give a very brief summary of the work that we have been working on for the last 3-4 years. And so recently we've been working on different things. One is to synthesize the result with continuous and diverse output. So we can, in our prior work, we could synthesize result with moving, but it turns out that the moving results are not very smooth. And the result, we also need to be somewhat meticulous so that we can generate diverse output. So in this work, we find better way to synthesize results by using assigned attribute vectors. And so that allows us to interpret result better. And so we also work on, similar to some recent work, we also work on attribute-based GAN model for image synthesis. And again, so there are some tricks. Well, we also find there are some limitations on recent work. And so we find an effective way to generate diverse output so that we can control the result with attributes. And another work that we've been working on is to speed up Singang. So we use, well, we use meta learning method so that we can synthesize result with one pass without, so typically with Singang, you have to train that for thousands of iteration, but with this method, all you need is just one pass and you can synthesize a result. And we also work on, say, suppose you have, just similar to the prior talks, so suppose that you have different contents, and then the question, how do you composite this image into and synthesize new results? And yeah, so finally, so another work that we've been working on, or we've been wanting to do is to synthesize results like this. So we want to mix the real and the synthesized image together. And this is basically inspired by an old MTV, the Take On Me by AHA. For some of you may remember this video, but likewise for this, and then we want to find a way so that we can synthesize result automatically. Okay, so yeah, so that's all I want to talk about today. So so basically we use fundamental tools for new methods. So we still use segmentation, geometry, consistency, object flow, and all that to synthesize content. And I want to thank all the collaborators, my students, and this is a joint. Well, the result presented basically based on their efforts. And that's all I have today. So I'm happy to answer any question you have.
Thank you, Ming-Xuan, for the great talk. Just want to ask, like, any questions from the audience? Like, we have one audience asking, like, whether you're gonna share slides.
Oh yeah, I can send it to you, and then you can put online and so on and so forth, or it depends on what you want to do. But the file size is large because I have video, so I just checked that it's about more than 550 megabytes, but you can put it somewhere for downloads.
Okay, we probably can put on the workshop website.
Sure.
All right, I don't see any more questions. Maybe it's also the time we can go to the. Oh, actually, there's one more question. Sorry about that. And the question is, what kind of data are you using for the Take On Me stylization?
No. Those are result. No, we just we want to do that, and we are not able to do that yet. But on the other hand, I forgot to mention one thing. We've been working on caricature. Well, we want to synthesize the result with caricature. So there are two ways to do that. One is that we just find some way to distort facial content, so that we can generate some caricature. And so the long-term goal is that we want to learn from masters. So we don't have enough data yet. We want to say we've been looking at the L. Hirschfeld's cartoon from New Yorker, but we don't have enough data, and so we would love to do that and then we can learn to draw different kind of cartoons or satire and all that. And so, but we need to find some data first, and then we can learn from that. But aside from that, we've been working on caricature, just distort some. We basically we can parse face images, and then we can find out eyes and nose and all that, and then we can generate some result with exaggerated attributes.
Great. Another question from Mingyu is, can you share more about a composite image synthesis?
So so I think in a month or so, we should be able to do that. And so Wei Long can also chime in on that. But basically we retrieve some contents and find way to put them together. But this works in review, so yeah, so we should be able to put it online in 1 month or so, in a few weeks.
Cool. Thank you, Mingxuan. Thank you very much.
Thank you. Bye-bye.
Bye-bye. I'd like to thank all the speakers. And now we will go to our oral and poster session for the accepted papers today's workshop. And I'm going to play a video from each of the author of the paper. Can you guys see my screen?
Hi, I'm Patrick, and I'll give you a quick tour of our work, Network Fusion for Content Creation with Conditional INNs. This is joint work with Robin Rombach and Björn Ommer from Heidelberg University. State-of-the-art models show great performance. However, they require massive amounts of computational resources. As a rough estimate, a single training run of models like BigGun, FUnit, or BERT take about 2 weeks, resulting in electricity costs of €300 or an equivalent of 400 kilograms of CO2 emissions. Note that this assumes that you already know the hyperparameters for your task. This goes so far, people have to join forces for crowd training to be able to train a single state-of-the-art model in slightly different configurations than the released ones. Thus, we ask ourselves how to optimally reuse the computational effort put into the training of these models. As an example, consider BigGun, which is great for class conditional image generation. However, what if we are interested in a slightly different task, like text conditional image generation? It should be possible to reuse the image generation capabilities of BigGun. Furthermore, there are also powerful models for representing other domains, like text in this example. Our main challenge is then to learn a translation between two representations produced by different domain experts. In general, this is a many-to-many task, as there are multiple realizations for a given query. Now that we have presented the general idea, we explain our method in more detail. Consider an expert model, which could be a classifier or a segmentation model, and split it into two parts. An encoding part, which yields a data representation, and a decoding part, which produces the output. Similar to expert 1, the second expert is also divided into two parts, which produce a representation and a decoding respectively. Note that both models are independent and can live on different domains, like text and images. Due to the many-to-many nature of the translation process, we propose to model the transfer between the representations generatively. Our idea is to use a conditional invertible neural network and formulate the translation process as a mapping from a predefined prior to the representation of expert 2, conditioned on the representation of expert 1. Let us illustrate the training process with the example of text-to-image translation. Given paired data, such as images and their textual descriptions, we produce their respective expert encodings. Next, the representation of expert 1 is used as a conditioning information to map expert 2's representation onto the prior distribution, where the quality of this mapping is evaluated by the log likelihood. During testing, given a representation of the first expert, here the sentence, "A yellow bird is perched on a branch," we sample from the prior and conditionally transform the sample into the space of the second expert. In our experiments, we show that our approach allows us to fuse BERT and BigGun into a text-to-image model. The resulting model is able to produce diverse samples with high interclass variability and also distinguish between more low-scale features, such as the color of a bird. Next, we exchange the BERT model for an image classifier, more specifically a ResNet. Based on the finding that CNNs trained on ImageNet are biased towards texture, we explored the representations of differently trained ResNets. For a vanilla ResNet 50 trained on standard ImageNet, we observed that conditioning on texture queries lead to coherence synthesis results, whereas conditioning on shape queries does not produce meaningful results. In contrast, using a ResNet 50 trained on a stylized version of ImageNet reverses this behavior. Texture condition synthesis produces unrecognizable image samples, whereas shape queries lead to the expected synthesis results. Based on these findings, it becomes evident that different synthesis tasks ask for different experts. Edge-to-image synthesis depends on a shape-aware expert, whereas for inpainting, a texture-aware model is desired and leads to the best results. Similarly, the choice of different layers of an expert gives control over the variability of the produced outputs. Finally, we evaluated our approach on tasks which work directly with labels. This is possible because we do not require gradients of experts. Our results show good qualitative and quantitative performance for face modifications and unaligned image-to-image translations. For more results, make sure to visit our project page. Thanks and enjoy the workshop.
Hello everyone. This is our presentation for our workshop paper, Text-Guided Image Manipulation via Local Feature Editing. My name is Tianhao Zhang, and this is a joint work with Lu Jiang and Weilong Yang from Google Research. So in this paper, we propose a new task called Text-Guided Image Manipulation. And the inputs for this task is an image and a text instruction. So we wanted to generate an output image by modifying the input image following the instruction given by the text. So here we have a text states that make middle right large cylinder small. And we have an input image where there is a large cylinder on the right part of the image. So we want to generate an output image where the cylinder is actually smaller, but the rest of the image are unchanged. The more well-studied area is image-to-image translation. So for our work, the core problem is actually how to apply text guidance into this image-to-image translation. And we wanted to basically use text feature as an operator to guide the image generation process. So here we propose a local feature editing method. Basically, we wanted to decompose the image generation process into two parts, finding out where to edit and finding out how to edit. So for where to edit, we wanted to highlight the region of the input image that needs editing. And for how to edit, we want to edit the highlighted area using the information given by the text. So take an example here. Given the text input make middle right large cylinder small, we want to use middle right to gain information about where to edit. And then we want to use make and small to get information about how to edit. And then we can first generate a spatial attention map to highlight the region that we want to edit. And then we can edit this highlighted region using how to edit information. Then we can generate the final image figure demonstrating the pipeline of the generator. Basically, the left part is the encoding part. And then the top right part is the spatial localizer. So we use the first self-attention module to get text feature for where to edit. And then we generate our saliency map M. And then in the middle bottom part, as you can see, it's the local feature editor where we edit the cropped image feature using the instance normalization parameters. And then we edit back with the unmodified part. And then we put the entire feature into additional ResNet blocks to generate a final modified image feature. And then we decode this image feature into RGB image. So we are testing our method on two data sets. The first one is called CSS dataset. It's a synthetic 3D scenes dataset generated using the Clever toolkit. And it's used originally for retrieval. There are multiple text operations, including adding, removing objects, and changing colors and sizes of objects. The second dataset is called Codraw dataset. Basically, it's derived from the abstract scene dataset, and it's used originally for iterative scene generation. And there is only one text operation in this data set, which is adding objects. So here we show a qualitative comparison. The first column is the input image and the second column is the input text. As you can see, our model can always generate the correct image based on the input image and text. However, for TA-GAN, it almost just copied the input image. And for Geneva, even though sometimes it can generate images with modifications, but the modification is not following the input text instruction. Here we also show some intermediate results. As you can see, the second row specifies to where to edit words. So it's the result of the first self-attention module. Here we highlight words with an attention score higher than 0.2. As you can see, top center, top left, these are all words for specifying the location. And the third column is the second self-attention module, where the words contain mostly how to edit information. And then the fourth column is the generated spatial attention mask. Even though it's a little bit blurry, but it actually specifies the correct location of the image that we wanted to make changes to.
This is Hong Rizhen from UC Merced. I'm glad to share our work, image synthesis via differentiable patch retrieval. In this work, we aim to generate images from the scene graph representations. Given the input scene graph, our model learns to retrieve patch for each object from the real images. Our model then synthesizes the final image according to the retrieved patches. There are two issues in our work. First, the retrieval process is usually not differentiable. Second, the selected patches need to be mutually compatible. Therefore, our contributions are in the retrieval process. First, we use the Gumbo softmax tree to make the retrieval process differentiable. Second, we design an iterative retrieval process to select mutually compatible patch. Here we show an example qualitative results. Since our retrieval approach can be optimized by the GAN training, we can synthesize more realistic images. Thank you.
Present star GAN V2, diverse image synthesis for multiple domains. Existing image-to-image translation methods require training multiple models or produce only a single output for each domain. To satisfy both diversity and scalability, one can give a latent code and a domain label to the generator and impose the latent reconstruction loss. However, in this setting, the latent code alone cannot contain domain-specific information. To overcome the problem, we introduce a multi-head mapping network. We transform a latent code into a style code using a specific output branch of our mapping network and impose the style reconstruction loss. Unlike the latent reconstruction loss, our style reconstruction loss models domain-specific styles. Our style reconstruction loss enables the generator to produce images with more diverse styles than latent reconstruction loss. Using style reconstruction loss, our star GAN V2 can successfully generate diverse images for all available domains. For more details, please visit our website.
Hi, I'm David, and in this short video, I will introduce our paper.
We propose a method for first generating a rough approximation of an image and then further fine-tuning it so that it's close to what a user has in mind. For the first step, text-to-image synthesis, we propose a new model called TextStyleGAN. We enhance StyleGAN so that it can generate images conditioned on text. For that, we use a text encoder, we apply attention on words and image regions, and we apply an additional multimodal loss to ensure semantic correctness. Here you can see some generated examples of this model. To manipulate a generated image, we use image representation W as features and training classifier to find semantic directions in latent W space. We then add these weights to obtain the manipulation. Here you can see some examples of manipulating images in gender direction. If you want to know more, check out the paper or feel free to ask me questions in the chat.
We present a new method for one-shot face reenactment. Given a face with target expression, the proposed StyleGAN model can produce realistic faces with required expression. Compared to the traditional face animation method, we only request a single image from source identity. We have no assumption about facial pose or viewing angles of input faces. We can also deal with complex background. After detecting facial landmark points, we feed both source image and landmarks to the model. The embedder learns to extract the pose information from landmarks, and then feed the feature to the transformer to transfer expression. Our results show that the proposed StyleGAN model can produce realistic reenact face with different source faces and target expressions. Thanks for watching.
Hello everybody, I'm here to talk about generating object stamps, and this is work primarily by Yusuf Majad. So our task is to take a background, which is not in the training set, and a bounding box, and then create an instance of a particular class. And we want to be able to give ourselves control over that class, such that we can manipulate the texture, such that it matches the lighting and the pose, and to be able to build up these scenes using objects of different shapes and textures. So how does this work? First, we have a shape generator, which takes in our background and the bounding box and infers a mask. And then we have a second stage, a texture generator, which also takes in the background here as a conditioner so that we can try to match the illumination of the object to the background. And you can see that we generate diverse shapes and that we have some control over the texture and that this matches the lighting too. Existing methods, like the Hong method, try to generate all of the interior of the bounding box at once. If we just try to copy and paste an instance with deep image harmonization, this typically tends to produce worse results too. Okay, there you have it, generating object stamps. Please come and talk to us. We'd be happy to start a conversation. Thank you.
Hello everyone, I am pleased to present our work learning to shadow hand-drawn sketches. This is the joint work with Suo Wuli at Project Hat and Dr. Adam Barkdal at UMBC. In computer graphics, cell shading is hard to get right, because the shadows must preserve binary appearance. It is either lit or not, nothing in between. It would be easily ruined by the smallest inconsistency. The goal of this paper is to shadow the given 2D line drawings automatically. The network builds the 3D information in latent space. The output of our network is just a pure shadow which can be edited by the artists. With our network, the artists can have a good starting point or a hint to shadow their art. We contribute a novel dataset which consists of 1,160 cases of sketch, shadow, and mask, but we didn't use masks in this work. We have 26 kinds of discrete lighting directions in this dataset. We use synthetic data to train a light pre-processing deep learning model to normalize the inputted line drawings, making them have the same line width. This is the general workflow of our network. The line drawings are inputted into the encoder first. The lighting directions are embedded by a fully connected layer. We repeatedly add the embedded lighting directions into each stage of the decoder. The final outputs are binary shadows as in our ground truth. We also have 2 intermediate outputs to facilitate the learning process. Both of them are soft shadows. The final outputs, S1 and S2 from the generator, are penalized by mean square error losses. We add a total variation term in the final output loss to encourage smooth shadow boundaries. The input of discriminator is the composition of shadow and line drawing in the lighting direction. The final objective is the sum of GAN loss and the loss of output S1 and S2. We build a relatively deep decoder to rebuild the 3D information in latent space. Whenever there is an embedded lighting direction inputted, we use film block to enhance the visual reasoning. When there is skipped connections from encoder, squeeze and excitation block is able to filter out the redundant information from encoder. The coordinate channel, which is marked as red after concat, is to enable the learning of 3D spatial information. At the end of each stage of decoder, except the final stage, a self-attention layer is added to enhance the holistic visual reasoning. We compare our work with Deep Normal and Sketch 2 Normal. The input of them are line drawings, the same as our input. However, their outputs are normal maps. To compare with our shadows, we render out the normal maps with thresholding at 0.5. Our results have accurate shadows in complex and multi-object line drawings. Also, our network learned the stylization of hand-drawn shadows while the others have the appearance that synthetic data has. When the depth of lighting source changes, our results have accurate and apparent shadowing changes. However, Deep Normal has inaccurate depth appearance in front lighting and side lighting, and Sketch 2 Normal suffers from complex line drawings. In backlighting condition, our results have rim light around object boundary, while Deep Normal and Sketch 2 Normal do not. We also compare with the baseline Pix2Pix and UNet that trained on our dataset. We can see that Pix2Pix architecture fails to reason the shadow, and UNet fails to generate binary shadows. Under the side lighting condition, we compare with a 3D test model ground truth. This picture demonstrates that Deep Normal has backlighting appearance when it is actually side lighting. Our result is most close to the ground truth and learn the smooth boundary of shadow from hand-drawn dataset. Despite the network learned from 26 kinds of discrete lighting directions, it can produce continuous shadows. There are more testing results in the wild in a wide range of style of line drawings. From the ablation study, we can see that, without the proposed modules in our network, the results will either have inconsistency, acne artifacts, or unrealistic shadows. Those are the failure cases and limitation of our work. First, we have slightly different shadows in different size of input. Second, if inputting a local part of an integral line drawing, the network couldn't reason the right shadows. Third, our network suffers with hard surface object. Last but not least, since our output is pure shadow, easy for artists to customize their own artworks like shadows in complex lighting source, have toned shadows in comic style, and concatenating colored line art with shadows. The last image is the original art drawn by an artist. This is another example of our shadowing system applied to reshadow the artistic line drawings. Thanks for your time. Please refer to our GitHub repository for the dataset and code.
Our work, Caligan, is a style and structure-aware Chinese calligraphy character generator. Chinese calligraphy is the composition of brush-written characters on paper or stylus. However, some characters become unclear or damaged when papers and stylus decay. This problem restrains calligrapher beginners from emulating masterpieces and designers from using masters' work. Therefore, we want to solve the problem of generating Chinese calligraphy characters. We form the problem as translating characters' image from one domain to another. However, existing method never exploit component information. Therefore, we modify a state-of-the-art GAN-based method by replacing its label embedding vectors by one-hot vectors and adding a component encoder. Experiments show our method generates better results. Our code and dataset is now public on GitHub.
Hi, I am Ayush from Adobe. I'll be talking about our work on image-based virtual try-on. The task of image-based virtual try-on involves taking as input the image of a target model, a new inch of cloth, and swapping in the cloth on the model to generate the try-on output. So a standard pipeline for image-based try-on consists of two phases. The first phase involves transforming the inch of cloth to align with the pose of the target model to generate a warped length. In the second phase, the warped cloth is transferred on top of the target model to generate the final try-on output. In this work, we proposed CVNet, a novel framework for image-based virtual try-on, and we break down the entire pipeline into 3 components, namely a coarse-to-fine warping component, a conditional mask generation component, and a texture translation component. These correspond to our warping and texture transfer phases respectively. So in this slide, we detail the network architectures for each of the 3 components. Next, we'll be talking about them in detail. The first step involves transforming the inch-of cloth into the warp plane. Now, to better handle fine-grained intricacies during this warping process, we regress the parameters of the spatial transformer network hierarchically in 2 stages, namely in a coarse-to-fine fashion. However, at inference, a single cumulative spatial transformation is applied on top of the inch-of cloth. Next, to better handle artifacts during the texture transfer process, we break down this phase into 2 steps. The first step, which we call the conditional mask generation, uses the segmentation mask of the target model and the image of the inch-of cloth to predict the resulting segmentation mask of the model after trying on the cloth. This mask is used as a prior to condition the final synthesis process of the try-on output. In the second step, called texture translation, we predict the final try-on output. This is done by using the conditional mask predicted in the previous step, the warped cloth predicted in the step 1, and a couple of texture translation priors. So these texture translation priors refer to components that are preserved during the virtual trial process and should be transferred as is. We train this translation network with a dual and triplet strategy, and empirical evidence suggests that training with this strategy helps to better handle bleeding and occlusion. We extensively compare our proposed framework CVNet with CVPR, a recent state-of-the-art, on a wide range of image quality metrics. Our extensive quantitative analysis highlights that CVNet consistently outperforms CVPR on all of the metrics. We also perform extensive qualitative analysis on a wide range of parameters. Our results show that CVNet is able to generate better quality of images, consistently handle occlusion better, generates skin better, as well as handle large variability in pose of the target model. Thank you.
Okay, thank you all for coming today. This is the natural language processing in Python.
No, it's not, everybody. It is still the AI for content creation workshop. You don't need to worry about that.
All right, I guess this is the end of the paper session. We're going. I'd like to thank everyone, every speaker, every paper author, and everyone come to the workshop. And thank you guys so much for participating. Yeah. I'm gonna hand over to other organizers to speak some.
Yeah. Yeah, thank you all for staying with us today. I think today we have many interesting talks, cover many different aspects of content creation, from 2D machine learning to graphics. So I hope you enjoyed the day. Okay. James?
At this point, the authors of the extended abstracts and papers have their breakout rooms. So please go and visit those and say hello. Try to treat it like a little virtual poster session. Pick the one that caught your eye and go and say hello to the authors. Otherwise, I'm very much looking forward to doing this again next year, but hopefully in person, so that we can feel a little bit more human rather than virtual.
And if you haven't done so, please vote for the best presentation. And
we'll just post the link again for that in the chat if we can.
Lou, do you want to say something?
Yeah, thank you for attending the workshop. I think I think I learned a lot. I mean, by looking at all the paper and speaker, and also I want to also thank the other organizer for the effort. I mean, it's not very easy during this time actually to organize such an event and to to accommodate different requests. Yeah, but hope to see you. I hope to see you next year and in person. Yeah, thank you.
Yeah.
Yeah. I again want to thank all the people who submitted their work to this workshop, all the invited speakers. This is great. I think all the content and the content creation workshop was fantastic. And I think another quick reminder, we are replaying the whole thing starting later tonight for folks who couldn't catch it. But if you feel like you missed something that you want to see again, you get another opportunity to see it in the second run. Right. Thanks.
All right. So there we go. Maybe I'll just leave the last word to Ziqing, given that he rounded up all of the organizers and did most of this. Special round of applause to Ziqing for that.
Thanks.
Yeah, cool. So I will stop recording. Hopefully the video will be available for the next round. Okay. I'll see you in the poster room.
Yeah, thank you.